everybody for coming. So I'm going to be talking about how matter gets recycled in the universe a little bit. So I thought that we would start with a very easy question. So where did everything come from? Okay, so by everything here, I mean the matter, the material that makes you, that makes me, the stuff in this room, the Earth, and indeed the whole universe. And as much as this question is clearly not easy, you probably all have heard it. It all started with
Big Bang.
the Big Bang. Okay? So the Big Bang is this huge explosion, right? That we think it happened 14 billion years ago. And that's where we think it was the start of the whole of the universe as we understand it today. Now you might say, she's sort of cheating because, you know, what banged the Big Bang? Right? Was there time and space before the Big Bang? Does it even make sense to do this question if time started with the Big Bang? Do other Big Bangs happen? And stuff like this? And I have an answer for you. I have no idea. But the good thing is that I don't think anybody in the world as an astronomer actually knows what's happening. Some people have theories, but we really don't know. What we do know, though, is that if you look for galaxies that are far away, all of them are moving further and further away from us. So the universe is expanding today. And we know, just by drawing it back, we know that the universe used to be smaller. How much smaller? Well, we think that 13.88 billion years ago, the whole universe, imagine everything that's here, was compressed in a thing that was smaller than the size of an atom, right? It was really, really tiny, and that was a fraction of a second after the Big Bang happened. And when, at that point in time, the universe was also very, 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 very hot. How hot, you ask? Well, it was this much hot, right? So it was 10,000 billion degrees Celsius. That's really, really hot. And when things are this hot, you can't form atoms, the units that makes our bodies and everything else in the universe, right? So at that point, what we have is what we call a primordial soup. So you have a lot of weird particles, quarks and neutrinos, and light particles, which is what we call photons, but you don't have any atoms. So to form atoms, you first have to cool down the universe so that quarks can make other particles that are called protons and things like neutrons, and then they can come up and form what we call an atom today. So you can imagine to go from this temperature to form atoms, it must take a really long time, right? Well, it took a really long time. It took 3 minutes. So in 3 minutes, the universe expanded exponentially very, very quickly, and it cooled down from this humongous temperature to temperatures that it can actually start forming nuclei. So we formed hydrogen nuclei and helium nuclei, and after a little while, electrons started rotating around this nuclei, then we had the very first atoms. And it was in these very first few minutes that we started forming all the first ingredients of everything that we see today in the universe, right? Now, the universe at the beginning was too hot, and it's like the Goldilocks story, right? First, the universe was too hot to form atoms. At some point, it was just right, and then after a little while, it was too cold. We couldn't form anything anymore, right? So there was this very short period of time in the beginning of the universe that the temperature was just right so that you could actually form the very first atoms. Now, because I'm going to be talking a lot of atoms and I want everybody to understand my talk, I'm just going to revise a little bit what is an atom. Okay, so this is my very realistic representation of an atom, right? I'm pretty sure that everything is this color and everything. So here in blue we have the electrons. So electrons, they have this little minus sign because electrons have an electrical charge that's negative, okay? So this is what creates the electricity in your house. You just have electrons running through wires and stuff like that. And inside this cloud of electrons, you have the center, which we call a nucleus, And the nucleus is formed of two things. It's formed of these particles that have a plus sign, and lo and behold, those are particles that have a positive electrical charge, right? And you have these gray particles that are neutrons, and they are neutral, okay? So they don't have either a positive or a negative electric charge. Now, what you have to understand is when it comes things that have charge and electrical charge, they feel electrical forces. And electrical forces, they work in a very nice way, because if they are the same, they don't like each other, right? So this is here represented also very accurately by these particles. This is two protons hating each other. But their electricity is not the only force that you have in the universe. And the funny thing is that if you take two nuclei and you start pushing them together, they are going to try to repel because they are the same. The electrical forces are trying to repel each other. But if you really squeeze them close together, then suddenly the strong nuclear force, it's another force that acts in the nucleus, and it just works that when things are very close together, then that kicks in. And then instead of hating each other, they go through loving each other. So they're very bipolar things. I wouldn't trust one if I were you. So that's what keeps everything. For example, you see that the nucleus is made of, so for example, this one is made out of 3 protons, right? So if it wasn't for this strong nuclear force, they would just go dancing away because they don't want to stay together. But because of this stronger nuclear force that works as a glue, then they manage to stay all compact in this nucleus. Now, there isn't one type of atom. There are many types of atoms. And we have the name that we give to a certain atom depends on the number of protons you find in the nucleus. So if you count here with me, 1, 2, 3. So this one that has 3, we call it a lithium atom. So the name that we give for every single atom that has a different number of protons in the nucleus is what we call an element. Okay? And you might have seen this before. So this is the periodic table, and this number here on the top shows how many protons each one of this type of atoms have. So if you have a hydrogen atom, then you have how many protons? 1. Okay, and if you are a helium?
2.
What about if you are something like gold?
7.
Yeah, okay. So you have like over 100 elements here, right? And each of them has a huge number of protons, or a certain number of protons in their nucleus, and that determines how they behave as an atom. But they are all made of this same stuff. They are all made of these electrons, neutrons, and protons, right? And in the Big Bang, what we got out of the Big Bang on that really nice time where the universe was just the right temperature is we got a lot of hydrogen atoms. So 75% of all the atoms that formed were hydrogen, 24% of the atoms that formed were helium, and just below 1% was lithium. So it formed these ones here. And then you say, wow, wait a second, you're lying to me, right? Because you said that the Big Bang created everything. And I know that I'm not made only of hydrogen and helium and lithium, right? I'm way more complex than that. I have carbon, I have oxygen, I have nitrogen. I mean, the Earth's surface also has a bunch of other stuff, right? You see iron, you see silicon, aluminium. So how did that all came to be? How can that be? Well, I have news for you. You're all recycled. You're all recycled stuff. So for you that don't like recycling, I would seriously rethink my concepts, right? So we're all somehow recycled material. And then you might say, well, wait a second, this is sounding too much like alchemy. I mean, you might have heard that in the Middle Ages people were trying to transform lead into gold, right? So if you're saying that atoms are all made of the same stuff, are you actually saying to me that I can turn lead into gold? Yeah. Yeah, the heck you can. Actually, we've done something very similar to it about 40 years ago. We didn't transform lead into, so gold is this one, lead is this one, is Pb because of its Latin name, which is plumbum. But we transformed bismuth, because that's just slightly easier, into gold. We actually managed to do that. Because it's just a question of you either putting more protons in the nucleus or taking protons out, right? Because that's what determined the atoms in this table here, right? So, and you're like, what are we doing here? Let's just go out and produce lots and lots of gold out of lead. We're gonna all be rich. We share it, right? The thing is, it would cost more than $1 quadrillion to produce 1 ounce of gold, right? By this method that we use. So it takes a lot of energy, it takes a lot of money to do stuff like that. It is not an easy process at all. And this was said by Glenn Seaborg. This has to be the best name for a Nobel Prize laureate. It just sounds like cyborg. Anyway, and this is like $1 quadrillion like 20 years ago. So taking into account inflation, really not economically viable. Okay, so yes. But that's a very important idea. So the idea is like, we can't do it because we can't do it efficiently. But maybe there's something else that can do this efficiently. So we need a recycling machine that changes things from hydrogen and helium and lithium into the things like carbon and nitrogen that we are made of, okay? So we need a stellar idea. Can anybody guess what I'm going for this? Yes, star! We have to study the circle of light, okay? Think a little bit about how stars work. And so what we might be seeing in the sky tonight, if it wasn't cloudy, is things like this. You might be able to recognize this is a constellation. Anybody knows? Shout out. Yeah? Orion, okay. So this is Orion's all nice and beautiful in the sky, and that's what you would see. This is the visible light. But if you were able to look with a telescope that sees in the infrared, or if you had really good eye vision and you put infrared, glasses in a certain way, then that's what you would see. So what you see here is that this space that looks completely empty between the stars is actually not empty at all. It's full of gas and it's full of dust. And this bit that is very, it's yellow and it's white, this is where this gas and the dust, they are very concentrated. You have a lot of mass in a very small amount of space. So we say that it's very dense, okay? And it's in those places that you have stars forming. So here, this one is what we call the Orion Nebula. And it's what we call a molecular cloud. So it looks like a little bit like a cloud because it's made of gas. And in the really dense bit, so here it's not the Orion, but it's another molecular cloud. But you can see it has like this dark places here, which just has a lot of gas and dust. And what happens, because it's very dense, because it has so much material, there's some other force that's important here, right? Something that works with mass. So that's the force of gravity. Things that are very massive have a huge gravitational force. So what happens is that gravity starts pulling this material together, right? And as it pulls the material together, the cloud gets hotter and hotter and hotter and hotter. And at some point it gets hot enough that it can start a process in the core that's called nuclear fusion, right? And then at that point is when you get a star. Now, what is nuclear fusion? Nuclear fusion is the way that stars came up to cook these other elements. So you remember that we had the ingredients, which were hydrogen and helium, and then the star is going to cook all the other elements from nuclear fusion. So you start from this very basic stuff, and what they try to do is they take one nucleus and try to bang into another nucleus and fuse them together. And then what happens if you have two nucleus together? So for example, if I had this nucleus joins another one just like it, then I'm going to end up, I have 2 protons, then I'm having 4 protons now. So I'm changing to a different element, right? The only problem with this is that the nucleus is positively charged, right? And the other nucleus is also positively charged. So you remember that they don't like each other, so you have to somehow make them go close enough together so that strong nuclear force can kick in. And that's why you need those very high temperatures at the center of the stars. Just so that things are traveling so quick that they don't have time to see that they don't like each other. They just go pew! And then they fall in love immediately, like love at first sight, okay? So that's basically how nuclear fusion works. So you can take lots and lots, for example, of helium and make something like a carbon. And in the meantime, you also release some energy. So that's my little wiggly thunderbolt there, okay? And why does it release energy, right? It's because if you take the nuclei that you started with and you put it on a scale, and you compare it to the nuclei that you ended up with after nuclear fusion, okay? And you put it on the other side of the scale. It turns out that the nuclei separated are actually heavier than the nucleus together. And then you're like, how? How can I get, 4 balls plus 4 balls, and then I have 8 balls, and the 8 balls are less heavy? How does that make sense? So what happens here is something very funny. So you might have heard of Einstein, maybe?
Yes.
Yeah? So he had that very famous equation that was called E equals mc squared. Yeah? Everybody has heard of that? So the E on the EMC squared is energy. The M on the MC squared is mass. And the C squared is just the speed of light squared. So this C squared is a really big number, right? So what that equation says is that you can take a little bit of mass and make it into a huge amount of energy, right? And that's what a star is doing all the time. So the star is taking 2 lighter nuclei and 2 heavier nuclei, making a slightly lighter nuclei, and the rest of the mass goes out into energy. So that's the light that you see from the stars. Okay, the light that you see from the stars is this small difference in mass that happens because of nuclear fusion that's just transformed into energy. And because you create this energy is able to contain the gravitational collapse of the star. So the star enters a sort of equilibrium. So in a certain way, gravity is pushing down. So it's like gravity is pushing me down to the center of the Earth, right? But the flood is offering a counterforce. So I'm in equilibrium here. So it's the same thing with the star. The star, part of it is pushing down gravitationally, and then this energy from the fusion is creating a pressure that's pushing it up and balancing it out. Yeah? Okay. So by doing this fusing, so the star just keeps there happily fusing nuclei, and then takes one slightly heavier nuclei, fuses with another hydrogen, and another helium, and another hydrogen, and it keeps building the elements on the periodic table. So it starts with lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on. And at the end, it looks a bit like, so if it's a very massive star, it's going to go and it's going to continue burning. It's going to very much look like a non. It's going to fuse one element outside, and then it's going to fuse other elements in the middle. So at some point, it starts fusing things into iron, which is Fe here, right? And at that point, the star faces a problem. And why is that? The problem is that nuclear fusion doesn't work for everything. So there is a point that your nucleus starts getting so large. You remember what keeps the nucleus together is this strong nuclear force, right? So at some point the nucleus is so large that one side of the nucleus can't really communicate very well with the nuclear force to the other side of the nucleus. And then instead of releasing energy, then they start to join 2 nuclei together. You actually have to absorb energy, right? So now if you put your atoms in a scale, it would be different. The joined nucleus would be heavier than your 2 nuclei that you started with. So you have to absorb some energy to form that, right? And that's, for example, so that also means that if a nucleus like this splits up, then it's going to release energy. So that's what we have for nuclear fission, right? So if you get like a uranium atom which has 92 protons, and you split it, then suddenly it becomes lighter and some energy is released. So the whole of nuclear fission works on this reverse process of nuclear fusion. And it turns out that the point that this balance turns out from one side to the other is exactly on iron. So up to iron you can join nuclei and you can release energy. After iron you have to absorb energy to join nuclei. Okay? And then what does that mean? It means that the star can no longer fuse this iron and release energy. If it can't fuse the iron and release energy, then there is no energy to contain gravity. I am not in balance anymore. So gravity just takes over and everything collapses. Right? And that's how you form from a very, very massive star, how you form a black hole in the middle. Or sometimes if the star is not as massive, then you form a neutron star. Now, as it collapses, it also heats very much. So the outer layers, they just expand into the universe into a huge explosion that we call, do you know?
The Big Bang.
Supernova. Okay? So then you go supernova. If we're going to have an idea of how great those explosions are, right? This is an entire galaxy. A galaxy with millions of stars, right? This is a single star going supernova. So in that point in time, one single star can outshine an entire galaxy. Think how amazing that is, how much energy it is releasing, right? And in this very energetic release, right, there's a huge shockwave. We go through a phase that we call a snowplow. So you know a snowplow, the thing that comes and gathers the snow? Yeah? So it's the same thing. It's so much energy, it's going so quickly that everything that there is, all the gas gets compressed in this very tiny layer with a lot of energy. And now we have a lot of energy. So we don't care anymore that we have to take energy to join two iron atoms. We can actually do it because we have excess energy. So then we can actually do in these very, very energetic supernova explosions by just getting more neutrons, we can just climb up all the periodic table and produce all the heavier elements. I say all the heavier elements. There are some elements that are only man-made, but you know, from nature-wise, then we can get everything else from there, right? So what happens then to all that was made in stars? Well, after you have a supernova, then all those elements that you produced during the time of nuclear fusion, as well as that time during the supernova where it created the very heavy elements, you know, that's released into the universe again. And then it can have time to cool down, and then it's going to create more molecular clouds, more of those clouds where we form stars, right? So you can get one molecular cloud like this, and then now because you have other heavier elements, then you can start forming other things other than stars. You can also start forming little planets. And maybe if you're lucky enough, then you can even form life, okay, like we have here on Earth. So it's all a big recycling machine. So you have these molecular clouds, you have regions that are very dense, they contract over gravity, they collapse into stars, and then eventually those stars die, release all the material of these elements back into the universe, and then it becomes molecular clouds again, and so on. Okay, so it's a huge recycling system that we have in the universe going on. And that's the end of my talk, and I wanted to leave you this quote by Carl Sagan, which you're almost sure to have heard at some point. The cosmos is within us, and we are star stuff. But the phrase that I like the most is this one. We are a way for the universe to know itself. Think about it. That's it. Thank you.